Hello everyone, I hope you all are doing well. I'm Fatima Jalil. I just finished my PhD from the Department of Chemical Engineering, IIT Delhi, and I've been working as a trainee teacher in the Department of Chemical Engineering, NIT Srinagar. I'll be presenting on biogas reforming for sustainable production of fuels and chemicals. It's a mechanistic study which was conducted using ab initio microkinetic model. Experimentally, the screening of large number of monometallic and bimetallic alloy catalysts is conducted via high-throughput methods. It basically involves the automated preparation of catalysts, followed by the catalyst characterization. Once the catalysts are characterized, they are then screened parallelly in reactors, and upon the completion of reaction, the products are then analyzed. Now, how this is done is basically, for the automated preparation of catalysts, there is either an automated liquid handler or by means of pulse laser ablation technique, a large number of catalysts are synthesized parallelly. Once the catalysts are synthesized, they are then characterized by means of various characterization techniques to understand their physical and chemical properties. These could be XRD, TPD, TPR, XPS, etc. Once the catalysts are characterized, these are then screened in monolithic multi-channel reactors, as shown over here, wherein each channel is filled with a different catalyst. Upon the completion of the reaction, the products are then analyzed by means of mass spectrometer. Once the analysis is complete, one can actually determine the activity and selectivity of different catalysts for the particular reaction. Well, this was the protocol for high-throughput experimental catalyst screening. In this study, we have demonstrated kinetic modeling as a tool to do this high-throughput screening. We have used kinetic modeling basically to understand the activity and selectivity of different catalysts without having to run actual experiments and do actual synthesis and characterization. Traditionally, the kinetic modeling is done via different models, by means of different models. Most common amongst which is the Langmuir-Hinshelwood model. It basically assumes that whenever the reaction takes place on the surface, the reactants come and sit on the surface, they get absorbed. The reaction takes place on the surface and the products of the reaction are then desorbed from the surface. There is generally an assumption of rate determining step. Basically, in order to draw models from experimental data, it is very important to make such assumptions because it is not physically possible to experimentally measure all the variables. So it's important to use these assumptions in order to make the model much easier to solve. However, over here, we have used mean field microkinetic model. And we have solved all the rate equations. We have not used any assumption of rate determining step or most abundant surface intermediate or nearly empty surface, which are basically the assumptions used to simplify models based on experimental data. The energetics which we've used in our modeling are actually derived from density function theory calculations. We've solved the different rate equations using steady state approximation, which assumes that the coverages do not change with time. Upon solving the kinetic model, it is possible to represent the turnover frequency, which is basically the production rate of different products formed with respect to some descriptor, which is generally bond strength. Now, if the binding strength is too strong, which means if the adsorbates bind too strongly to the surface, the reaction rate would lie on the left side of the plot, which is this is basically Sabatier plot. It will lie on the left side, which means the reaction will be desorption limited. However, if the binding strength is too weak, which means the adsorbates are not able to adsorb properly to the surface for the reaction to take place, the reaction will again be limited by the dissociative adsorption rate. There is a fine balance between these two opposing forces, and when the catalyst has that right amount of binding, it will lie at the top of the Sabatier plot, wherein the binding is just optimum, which means it's neither too weak for the reaction to be adsorption rate limited, nor is it too strong for the reaction to be desorption rate limited. We have done this microkinetic modeling using CatMAP, which was a tool developed at Stanford, California. Herein, all the rate equations are solved for steady state approximation. It's a mean field microkinetic model. However, we have not represented our system by a single descriptor, as was the case for Sabatier plot. Herein, we use two descriptors, which is the oxygen as well as the carbon binding energy. on the surface of transition metal catalysts. This has been possible only by the means of transition state scaling relationships and absorption state scaling relationships, which basically represent the energy of the absorbed state as well as the transition state with respect to these descriptors. We have implemented this microkinetic modeling on biogas reforming reactions. Basically, what is biogas reforming? Biomass upon anaerobic microbial digestion results in the formation of carbon dioxide, methane, water, and some trace amounts of oxygen and nitrogen as well. Now, in order to use this biogas, it's not possible to use it directly as fuel because of the presence of carbon dioxide, which reduces the calorific value. Secondly, it is not possible to separate carbon dioxide from this mixture as it will be a cost-intensive process. So a way forward could be the reforming of this biogas towards the production of syngas, which includes carbon monoxide and hydrogen, which can be further then converted to different fuels and chemicals. The reforming reactions which take place in biogas reforming are the dry reforming and the steam reforming. Dry reforming reaction is the reaction of methane with carbon dioxide, whereas steam reforming is the reforming of methane with water. As can be seen over here, the reaction of methane with carbon dioxide produces a different ratio of syngas as compared to that of steam reforming. There have been some previous experimental studies on biogas reforming. This one was done by Ola et al. On bioreforming of methane. This is basically a particular combination of steam and dry reforming wherein met gas is formed, which means the CO is to H2 ratio is that of 1:2. And these are then further processed towards methanol and hydrocarbon synthesis. One other example is the CO2 conversion to syngas through steam biogas reforming process. Over here, the authors observed that the methane conversions were actually much higher as compared to CO2 conversions for the process. In order to understand the mechanism of biogas reforming reaction, we constructed a microkinetic model, taking into account all of these reactions which may possibly take place. The reactants are basically methane, carbon dioxide, and water predominantly, which result in the formation of CO and H2, which is the syngas, which can then further be processed to higher fuels and chemicals and different hydrocarbons, basically. The model was constructed over the 111 terrace sites, which are flat surfaces, and 211 step sites, which show a higher level of under-coordination. The model also included the formation of coke, as that is an important issue in biogas reforming processes. CC coupling reactions were considered to understand coke formation. C star, which is absorbed carbon, can couple with another C star to form C2, which combines with C2 again to form C6, which was considered to be coke. In biogas reforming, there are basically a number of coking mechanisms which may take place. Two important ones, basically two predominant mechanisms, are methane decomposition and Woodard reaction, which have been observed to take place experimentally. Now, methane decomposition is basically the direct decomposition of methane towards the formation of coke and hydrogen gas, and Woodard reaction is the decomposition of carbon monoxide towards the formation of coke and CO2 gas. And in order to understand the coke formation, we solved the model for the steady state approximation at the temperature of 973 Kelvin, and this is the coke production plots which we obtained. These plots are showing the coke production on 111 as well as the 211 sites of the transition metal catalyst. It can be clearly seen that the maxima for 211 sites is actually 2 orders of magnitude higher as compared to that for 111 sites. Nickel is showing the highest turnover over the 111 sites, which is of the order of 10 per second, whereas on 211 sites, platinum, which is showing the highest turnover of 10 to the power 3 per second. It can be easily discerned that step sites are showing higher propensity towards coke formation as compared to that of terrace sites. To understand the coking mechanisms, we then explored the consumption rates on the different sites of the transition metal catalyst. The one shown over here is the consumption rates on terrace sites. wherein the consumption of methane, carbon dioxide, and water are shown on the 111 sites of transition metal catalysts. It can be seen that methane consumption rates are actually higher as compared to CO2 and water consumption rates, which is basically suggesting that methane is undergoing some other reaction besides the reforming reaction. Also, water consumption rates are higher as compared to CO2 consumption rates, which is suggesting that there is a higher rate of steam reforming as compared to the dry reforming process. The coinage metals are not showing appreciable turnovers. Importantly, all metals except cobalt and ruthenium are actually showing significantly reduced CO2 and water consumption rates as compared to that of methane. We further analyzed the consumption rates on step sites. The methane consumption rates are actually much higher as compared to 111 sites, except for nickel, wherein the methane consumption rates remain the same on both the sites. CO2 consumption rates are unusually lower, which basically suggests that step sites do not show much occurrence of the dry reforming process. Overall, the methane conversion rates are higher on the step sites. Similar observations have been made experimentally. This work was done by Rostrup-Nielsen. This basically shows that the steam reforming process, which is the first column, is showing higher turnover as compared to the dry reforming process, which is similar to what we observed in our study based on both the step sites as well as the terrace sites. Furthermore, one other study showed a similar trend. Over here, they observed that for steam reforming process, the maximum CH4 consumption was 60%, whereas for dry reforming process, the maximum CH4 consumption was observed to be 30%. This is basically indicative of the fact that dry reforming rates are actually much lower as compared to steam reforming rates. Yet another study which corroborates our understanding from our microkinetic model is this one. Over here, they show that methane conversions were actually much lower or much higher as compared to the CO2 conversions, which is similar to what we saw in our volcano plots. To further understand the biogas reforming process, we analyze the production rate of coke, carbon monoxide, and hydrogen gas on the surface of transition metal catalysts. These are the production rate plots which we observed for 111 sites. It can be seen that nickel, rhodium, platinum, and palladium are lying in the center of the coke volcano plot, which means they're susceptible towards coke formation. However, as we had observed previously that methane was showing higher conversions as compared to CO2 and water consumption rates, which was indicative that methane was undergoing some other reaction, which is basically the methane decomposition reaction towards the formation of coke. That is why such high amounts of coke are being observed in these transition metal catalysts. Further, it can also be seen that hydrogen production rates are much higher as compared to CO, which means hydrogen is actually being produced by some other process besides reforming, which is the methane decomposition process. Platinum and palladium exhibit less of reforming, as they're forming a lot of hydrogen, but not enough CO, which means they are undergoing a greater degree of deactivation. Nickel and rhodium, besides producing syngas, are also producing a lot of coke. It can be seen that it's just cobalt and ruthenium which are producing equivalent amounts of CO and hydrogen and are not that susceptible to coke formation, which means that they could be potential catalysts for the process. Analyzing the production rate plots in 211 sites, it can be easily seen that the production of coke, CO, as well as hydrogen, all three are much higher on step sites. But because a lot of coke is being formed, it means that the step sites are not stable for this reaction. The extent of methane decomposition is actually much higher on step sites as compared to that of terrace sites, which means most of them are actually going towards coke formation. And platinum and cobalt exhibit increased rates of SRM, but besides that, they also mostly undergo coke formation process. Basically, they are being covered by coke. We further analyze the selectivity plots for biogas reforming reaction based on different metrics. The first one was the Syngas ratio, which is the ratio of H2 to CO being formed in the process. As can be seen over here for 211 sites, all the active transition metal catalysts are showing higher rates of H2 formation as compared to that of CO. which is basically the cause of the methane decomposition route, resulting in the formation of coke. However, on 111 sites, cobalt and ruthenium have a ratio of syngas which is close to that required for Fischer-Tropsch reaction. One other metric which we used was coking propensity, which was determined by the ratio of methane consumption to coke formation. Now on 211 sites, it can be seen that for all the transition metal catalysts, the active ones, the ratio is close to 1, which means most of the methane is basically going towards coke formation. However, that is not the case for 111 sites. On 111 sites, it can be observed that cobalt and ruthenium show the ratio of CH4 to coke formation to be equal to somewhere between 2 to 3, which means methane consumption is actually much higher as compared to coke formation, suggesting that besides coke formation, other reactions, which is the reforming reactions, are also taking place. Finally, the most important metric to do the selectivity analysis was CO formation, which is carbon monoxide formation versus methane consumption. It can be seen that for both 211 as well as the 111 sites, it's cobalt and ruthenium, wherein the ratio of CO to CH4 is the closest, which means CO formation rates are similar to that for CH4 consumption rates. And they're more similar in case of 111 sites as compared to that of 211 sites, suggesting that cobalt and ruthenium are the best catalysts for the process. Based on this analysis, we can see that cobalt and ruthenium have been identified as potential catalysts for the VGR process. Furthermore, Terrace sites have been identified to be more stable as compared to the step sites for biogas reforming process. We also did some classification based on the CO formation versus CH4 consumption rates, wherein cobalt and ruthenium lied in a single category, which was the potential catalyst, and rhodium and nickel, which showed similar selectivity, lie in the class 1. Similarly, the coinage metals form another class, and platinum and palladium, which are doing more of coke formation and reforming, lie in class 2. The way forward in Silico high throughput screening is basically using machine learning. The kinetics, the energetics which we used in the microkinetic model developed over here, used the binding energies or the descriptive energies from density function theory calculations. The way forward could be that if we could use machine learning to determine the binding energies or the descriptive energies, that could save up on a lot of computational time and even computational cost, which is involved in doing density function theory calculations. We actually implemented the machine learning to determine the binding energies of single atom alloys of copper, which can be seen over here in this periodic table. Machine learning, if combined with density function theory calculations as well as microkinetic modeling, can help in the prediction of kinetic trends for larger molecules and for large number of reactions. Finally, I would like to thank my supervisor, Professor Ali Haider, for always helping me out. I would like to thank Dr. Tuhin for helping me understand kinetic modeling, Dr. Imtiaz for always being there for help, Dr. Uzma and Dr. Shalaka. I would like to thank HPC facility IIT Delhi, NIT Srinagar, and my lab mates at the REC lab. I hope you all enjoyed the presentation. Thank you so much.